Pamela.
That was louder than you were while we were prepping.
It shouldn't be. What? No, it just didn't hear me for a while. It was like listening. Where's Fraser? Listening. And then it jumped up. So, hey, happy Memorial Day.
It's Memorial Day here.
Awesome. I mean, of course, it's a week after Victoria Day, but.
And it always sounds weird to say happy celebration of all of the people who died trying to protect our freedom.
Yeah, so, a somber and memorable,
reverent. I'm not sure.
Memorial Day. Yeah. No, I know. I was trying to think of like how do you say ours is Remembrance Day. We have ours in November, but well, I hope you're having a quiet, contemplative day at home today. So anyway, this is Astronomy Cast. Fraser Kane, that's Pamela Kay.
Hi.
We're going to take an hour of your time and educate you about physics and the interior of the atom. So just to remind you all, this is a live interactive experience. You can go ahead and post any questions that you might have for us, and we will try and get around to them until after the show. So I'm going to say hi to Graham Ash and Douglas Friday and Tony Lynch and Tom Van Scotter and Dusty Reichwin and Peter Waldman, Guido Bibra and Thomas Traniker and Nancy Graziano and Albert Braun. Hey, everybody. And those are just some of the few people who jumped in and posted a question. And the question was, hi. So...
this reminds me of George Hrab's song, Make Sure Your Question is a Question. We love all of you, but it still reminds me of that song.
Yeah, well, they're very good about it. So in the Q&A app, they all just make one hello post, and then that's it. And then all the other conversation happens over on the event page. And then any questions that they have, they actually post into the Q&A app. So so we'll stick around and answer some of your questions about space and astronomy. Anything else we should let people know about this week?
Not that I can think of. We are gearing up to do, some of you may remember growing up or may still have kids that are participating in this, the Scholastic Summer Reading Challenge. We're going to do instead a Summer Science Challenge. Over at CosmoQuest, we're going to challenge you to complete a bunch of science, and
nice.
We'll have prizes for the people who participate.
Fantastic. All right. Well, let's just get going with the show then. I'm ready to record. Are you ready to record?
Yes. I'm remembering mono this week. Okay. I am ready to press record. Are you ready to press?
I've already pressed record.
Okay. Well, now I've pressed record too. Hi, Preston.
All right, here we go. Astronomy Cast, episode 378, Rutherford's Atoms. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos. We help you understand not only what we know, but how we know what we know. My name is Fraser Kane. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville, and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Good. So we think that people should do some science this summer.
Yes, we do. Over at CosmoQuest, we are doing a summer of science to get people using their brains as well as going out and enjoying the sunshine. So we're going to have a series of challenges for you starting June 4th, and we're going to have a variety of prizes for participants. So go get involved.
That sounds awesome. I'll get the kids to do it too.
Sounds great.
All right, so physicists knew the interior of the atom contained protons, neutrons, and electrons, but they didn't understand exactly how they were organized. It took Ernest Rutherford to uncover our modern understanding. So what time frame are we talking about now?
So we're still in the 1890s and early 1910s, or up through the early 1910s. So Ernest Rutherford was actually a student of Thomson's, who we talked about last week. And this is someone who kind of personifies the idea of the nomadic scientist. He was born in New Zealand. Parents were from England, but he was born in New Zealand, originally went to church on the South Island, not church. He originally, Christchurch is what I was thinking of. He originally went to university on the South Island, then was able to continue his education on the North Island in Wellington, got a scholarship to be one of the very few people allowed to study for an advanced degree at Cambridge without getting an undergraduate degree at Cambridge. Worked there under Thomson for a while, and then went to McGill University in Canada, and all the time chasing the ability to do more and more science.
And so, Thomson, of course, we talked about last week, he was the one who really started to puzzle out the nature of the electron. So when Rutherford kind of got into the act here, what was the state of scientific understanding of the interior of the atom?
Well, it really wasn't yet. We were actually at a point where people still considered atoms as these immutable basic building blocks of everything that couldn't change. Alchemy was considered something that would never be possible. Now we know that alchemy in terms of being able to make gold out of things isn't possible, but if you bombard something with enough neutrons, you generally can change its identity. But at this point, the idea that radioactive decay actually changed the nature of an atom didn't exist. The idea that one of the reasons the Earth is warm is due to radioactivity didn't exist. The idea that the sun was potentially powered through radioactive interactions, in this case, the hydrogen building to helium, and so forth and so on, the proton-proton chain, none of those ideas existed. And then Rutherford came along.
And so, I mean, what was the idea then? They thought that the atom were just like little balls of whatever the thing was. Like if you had gold, a block of gold was made of a bajillion little gold balls. And if you cut it down to the smallest piece, you ended up with one.
Yes.
One little gold nugget.
And they were starting to get the idea of protons, but not really. It was actually Rutherford who in the 1900s would go on to name the proton, name the neutron. But they were starting to get the idea that there were certain fundamental particles. And this was where Rutherford really started to come in. He did work on radioactive materials, realizing that through some basically, if you left a block of radioactive material that was the right radioactive material in a container, it would end up coating the container with something that he called thoron. It's a isotope of radium. So here he was starting to realize that nuclear reactions could produce a byproduct. He started to classify what are the different particles that come off during various radioactive decay processes. They were still trying to figure out what was going on, but he was the first person to start to figure out that the alpha particle was helium, that the beta particle was tied to a reaction where you ended up with high-speed electrons coming off in decay processes. Neutrons were a thing, but it was actually one of his students that figured out what the neutron was in 1932. So they were starting to get at these ideas of these things existing, but they didn't fully get there.
So you mentioned that he saw the substance that was the thorum.
Yes,
thoron, right. So what kinds of experiments did he perform to try and uncover some of the nature of the atom?
He did a little bit of everything. He was one of these people that he just kept trying things to see what would the byproduct be. So for instance, he was one of the people that worked to try and figure out how do you stop alpha particles? How do you figure out what alpha particles are? And he initially gave the alpha particle, the beta particle, and the gamma ray their names. And then he figured out that the alpha particle was actually just helium. So he was the one that figured out that. He then went on to start to figure out actually the reaction that we use in the modern smoke detector to figure out that there's a fire in your house. He was the one who figured that out. If you take a bit of americium, which is what we use right now, he used a different radioactive material. You can create a chamber with a positive plate and a negative plate that have clearly charge built up on them. They're connected with a battery. And if you put a small bit of radioactive material in them, that small bit of radioactive material will ionize the gases inside the chamber. And that ionization process will cause charge to flow between the plates, and you can measure this current. Well, what he discovered was if he blew tobacco smoke, because being a man of his time, he smoked, if you blow a bit of tobacco smoke into that ionization chamber, it will stop the current from flowing because you've disrupted the ions. And it was realized, hey, this is actually a way to detect smoke. So smoke detectors, actually, thanks to Rutherford.
That's awesome. But one of the most famous ones, of course, is the gold foil experiment, right?
Which actually isn't what he got the Nobel Prize for.
Yeah, well, that seems to go around. That's sort of the same thing happened to Einstein. So here's your Nobel for the photoelectric effect, as opposed to here's your Nobel for relativity.
Right. So he got the Nobel Prize for his work on figuring out radioactive decay, for figuring out that atoms do transmute into other types of atoms through nuclear decay processes. He started to figure out the idea of the half-life, and then got the 1908 chemistry Nobel Prize for that. And he was always a bit bitter that it was the chemistry Nobel Prize instead of the physics Nobel Prize. But having completed this work that got him the Nobel Prize and did neat things like allow us to understand that the Earth actually is really old, having done all of that work, he then went on to try and figure out what's up with the atom. He was one of J.J. Thomson's students. He understood Thomson's plum pudding model of the atom. He actually went on to replace Thomson as the Cavendish Chair at Cambridge, leaving Canada to go back to England. And once he was there, he started working with his graduate students, who are actually the ones who, as always, did the experiment that he gets all the credit for. And his graduate students set up a situation where there was an extremely thin piece of gold foil, and they fired a beam of electrons at the extremely thin gold foil and looked to see how those particles would be deflected, and found that the deflection actually matched with the idea of gold foil being made up primarily of itty-bitty little tiny spheres and a whole lot of empty space. And this finally got us to the idea that the bulk of the material in the atom is in the nucleus, which is surrounded by a cloud of electrons.
Right. We talked about this a bit last time, right? That if the you could imagine the atoms themselves, and if they were like a cube, for example, and you fired your beam of electrons, the electrons would all just come bouncing back because it was just like a wall of cubes. But if it was like a very large ball, then you would expect the beam of electrons to be bouncing off in various directions that would really compute with it hitting a sphere. But but if it was a very small but still kind of nugget at the very core of what was the atom, most of them would just pass right through, but some would deflect, and they would deflect as if they were ricocheting off this little tiny sphere at the middle of what would be the atom. And this is what they found.
Right. So he was doing this work in 1909, the year after he got his Nobel Prize. And this was basically what went on to completely change how we see the atom. And it was kind of a done deal at that point. So what was neat is he systematically went through and completely changed how we view the atom. We went from having no real understanding of its structure to Thomson thinking, well, maybe plum pudding idea, to Rutherford saying, no, it's actually this structure that is concentrated in the center. He then went on working still with his graduate students to start to pull apart the constituents of the atom. So in 1920, he postulated that the hydrogen nucleus, so take a regular everyday hydrogen that doesn't have a neutron, that's deuterium, it's still a form of hydrogen, but take a most common form of hydrogen, the one that doesn't have that neutron. strip away its electron, ionize it. What's left, he dubbed the proton. And so now we have this idea that atoms are built of something else. And this built on the work that he did in 1919 that showed that nitrogen bombarded with an alpha particle can lead to oxygen and something. That something was the proton. He started adding up the bits, starting to understand protons, how they add together to build up through the periodic table.
It's sort of I guess I'm trying to think about like what it must have taken for him to kind of make that realization, right? That hydrogen, which is sort of this most abundant atom in the universe, although maybe they didn't know that at that point, but that is the building block. You can kind of imagine that it would be something else, that it's all made of some other building block, even hydrogen, all the way up to whatever the heavier elements are. But in fact, that the lightest element is the building block that makes up the rest of the rest of the elements. I think that's a pretty monumental discovery.
Well, and then to go on without any observational evidence, because we just weren't quite there yet, to in 1921, while working with Niels Bohr, he postulated the existence of neutrons. So here's this person who through his life has just one after another figured out these key issues in the atom, figuring out what the different types of radiation are, how nuclear decay processes work, figuring out what are the constituent materials. He jokingly referred to himself as the first alchemist in trying to figure out how the radioactive decays happen. And what was also kind of amazing is it seemed like everyone he worked with went on to get a Nobel Prize. He simply managed to surround himself or be lucky enough to be hired into situations that surrounded him with the most brilliant people of his time. And he was just a farm kid from New Zealand. He wasn't a aristocrat. He wasn't noble born. So he was also one of the first scientists to essentially rise up out of nowhere to be one of our leaders of understanding.
Yeah, it worked with Heinz Geiger, one of the people who
was one of his graduate students.
Yeah, worked on radioactivity. Got some of his radioactive stuff from Marie Curie. Really like part of the Justice League of physicists, right?
When he was at McGill, he worked with Frederick Soddy, who went on to get the chemistry Nobel Prize. Just person after person that he worked with got the Nobel because they were literally redefining how we understand the microscopic, at the atomic level side of our universe.
So I'm sort of. Again, so he's gotten to the point that he's discovered he has predicted the neutron, but it actually took a long time for anyone to actually find it, right?
Right. It wasn't until 1932 that one of his graduate students actually was able to figure it out, James Chadwick. And we have an entire episode on that back in the first or second year of Astronomy Cast. But it was actually really difficult to figure out, and it took being able to create a stream of alpha particles to bombard beryllium, causing the beryllium to give off the neutrons. And for whatever reason, this is one of those scientific experiments that leaves me perpetually baffled. They figured out that if you put a block of paraffin wax into the stream of particles coming out of the beryllium that's being bombarded with essentially helium, that the particles hitting the paraffin will cause protons to be given off. And they were able to figure out, based on this really mind-blowing to me experiment, that the neutrons must have the same mass for the most part as the protons based on conservation of momentum. but since they didn't detect any charge, couldn't deflect things, that this was somehow a neutral particle.
Just mind-bending. Oh, right, Niels Bohr. He was working with Niels Bohr when he, when he came up with this theory for the neutron. So again, just another of the superheroes of early physics. It's also kind of amazing to me when I think about sort of where we are now. I mean, if he was working in the teens and the 20s, really in the 20s, when he really postulated the modern concept of the atom, and the confirmation really wasn't even made until the early 30s about the neutron. We haven't even hit 100 years this. It feels like we've known about the atom forever.
No, it's all entirely new. And what gets me looking at this is he was someone that also went on to try and do good things in the world. So he was someone that when he went to Cambridge, by the terms of his scholarship, he couldn't marry his sweetheart. So he left his fiancée behind in New Zealand. They got married and had a child when he moved to Canada. And throughout his life, just the importance of family comes up. When he moved back to England during World War I, he switched over his work to try and figure out not how to build bigger, badder weapons, but instead he worked on the sonar to try and understand how do you detect submarines so that there's less death. So he worked on sonar for a time. He was also part of the group that worked to try and bring as many scientists over to England as possible to protect them during the war. So over and over, he's working both on the let's do amazing science, let's raise up our students, let's get our students Nobel Prizes while we're at it. But he's also just a good citizen, and you don't hear stories like that very often in science.
Yeah, I hope our New Zealand fans are proud of Mr. Rutherford.
They put him on their currency.
There you go. I think we've got we've got Mark Garneau on our currency. We've got an astronaut on our 100, our 50. Yeah. Okay, so I just want to sort of close this up then, in that, when Rutherford was done with the atom, what was his understanding of what it was then?
He actually got us pretty much all the way to our modern understanding of the atom, that you had a central core that was made up of protons that defined the identity of the atom, that if you change the number of protons, you change the identity of the atom. This is where his joke about being an alchemist came up. He was the one who got us to the understanding of what the three kinds of radiation, alpha, beta, and gamma, that are the predominant forms of radiation are. He was the person who understood that there probably is this additional neutral component that goes into all of this, the neutron. He also started to make headway on what is the half-life and how radioactive material plays a role in keeping the Earth warm, how it's the potential fuel for the sun that allows the sun to be old. And there's the whole problem running up to that of is the sun powered by, they used coal to come up with calculations on how old the sun could possibly be. It was Eddington who eventually figured out the proton chain kinds of reactions that actually power the sun, but it was Rutherford who opened the door for nuclear reactions to be part of what allows things to last as long as they do.
So what do we then know now that maybe Rutherford didn't know specifically about the atom? Like when they thought the electrons were still kind of orbiting around the atom, right? They didn't understand the sort of modern concept of more of a cloud of probability, right?
Well, they were actually getting, that was all at about the same time. They were getting to the energy level ideas. They were getting to the discrete energies. They were getting to the Pauli exclusion principle. All of these things were coming up simultaneously throughout the world. And it was really this amazing age of invention's not quite the right word, but I guess intellectual revolution, in terms of finally having the pieces of the puzzle that were needed to see what the big picture was going to be. What's kind of sad is he actually died quite unexpectedly and fairly young in 1937 because he was too busy to get a hernia treated. So here you have this case of, I mean, he really kind of personifies all that's right and all that's wrong with science. He, like so many scientists, was the vagabond who moved from nation to nation trying to find the best place to get an education, the best job to take, put off getting married because that was what was required for the work. His health was not that great because he had a hernia, but he couldn't be bothered to take time off to take care of himself because there was the science. And it's just sort of like, this is all that's right and all that's wrong with science even today.
So if you're a scientist and you've got a hernia, you should go get that looked at?
It's true.
Yeah, exactly. Man, I had another question and I completely lost it. Oops. Damn. Oh, right. Okay, that's right. There. So, I mean, I guess one of the kind of the other tragedies, or not, the tragedies that they didn't have the tools necessary to start to kind of crack deeper into the atom, right? That we in our modern times know that there's a whole other layer going on underneath the protons and the neutrons and all of that you can actually break those things open, and there are more parts underneath.
And that's true. People do talk about how he was the first to split the atom in terms of getting an atom to decay into multiple bits that he could study. But the whole idea of the modern atom smasher that allows us to get at all the different additional particles that are out there, all of the unstable particles, all of the quarks that build up to create the proton. Bosons were something we still hadn't really figured out. The idea that the nucleus is held together using, gluon bosons. All of these things, we weren't there yet. But he got us to the point that we could see the need to figure those things out.
Yeah, it's almost like finally getting a sense of what the landscape actually looked like. So really starting to see, like, okay, now I understand what this looks like. And then the next question is to again go, why? Why are they connected in the way they're connected? What are the forces that are bringing them together? What is keeping, and as you said, with the Pauli exclusion principle, with some of those other concepts, are starting to really get a sense of what's going on in the overall environment, and why can't electrons share a quantum state, right? Things like that. And so they're starting to really get a sense of what are all the underlying rules and relations between these. Sort of the same kind of work that Einstein did, right? To kind of say, well, like, why are things attracted by gravity? What's really going on here?
Well, they're actually, I'd say, different sides of the problem. You have Einstein, who was purely a theorist. His ideas came from looking around, thinking hard, working out the maths. Rutherford, on the other hand, was someone who was considered perhaps the best experimentalist of his time, who systematically throughout his life, even as an undergraduate, he was working on incredible experiments where he was at the time working to figure out radio and how to detect electromagnetic radiation over great distances. He was working on X-rays. He was someone who poked and prodded at the world, trying to get it to give up its secrets. He wasn't as interested in theorizing what must be out there as he was at saying, okay, let's figure this out by actually looking and taking it apart whenever we can.
Yeah. And even to this day, right, it's still the experimenters and the theorists working hand in hand, who push the boundaries out. The experimenters who find that's funny, and the theorists who try to work out what's going on, or the theorists who try to provide some kind of path to search for the experimenters to actually go look over here, go look over there, see if you see this.
And it is that constant back and forth dance where the theorists have to match our current understanding of reality and then make predictions on what we're going to find into the future. The experimentalists, well, they're the ones out there trying to dig into reality and either prove or disprove the theorists or extend our understanding further so that the theorists have to again play catch up. Rutherford was someone who extended things further, requiring that catch up to take place.
Yeah, amazing. All right, well, thanks, Pamela. We'll see you next week for, I think, the final installment of our famous experiments series.
Yes.
All right, we'll talk to you next week.
Talk to you later.
Okay, we'll save that.
Oh, I'm still losing my voice.
Yeah, I know. I can hear it going. You saved the cough.
Yeah.
Till the very end. All right. Just 1 second, everybody, and then we will get on to the next portion of this episode of Astronomy Cast.
Trying to find, there it is.
Save, export. Come on. Done. And now upload. And then I have no more responsibilities today.
That must be nice to run out of responsibilities so early in the day.
I say that ironically. I got a question for you. If you had unlimited budget and unlimited access to education and resources, would you be an experimenter or a theorist?
I would never be a theorist.
You would never be a theorist? You would always be an experimenter?
Yeah.
Yeah? So if you were an experimenter, I mean, you kind of are, right? I mean, when you look at what we're doing with Cosmic Quest, with moon mappers and things like that, right? That this is, this is the experiment. We are looking for gathering data about the shape of craters on the moon, and then that's something that researchers can then use to answer some of their questions, right? Hey, I wonder if this impact zone is older than that one, and then they can get the answer. So so that's all experiment, I guess. What question would you, even with bordering on magic technology, what kind of experiment would you like to run if you could?
Oh man. I'm still perplexed by the fact that we understand so little of the details on stellar evolution. I'd really love to go back to the research where I started and work on trying to understand the details of stellar evolution using variable stars. And nowadays, the same data sets that you can use to find exoplanets, you can also use to study variable stars in much greater detail. But a lot of times they throw that data out just because we don't have the budget and the bandwidth to deal with all that extra data. And I want to leave no photon behind. And
so seriously, people are throwing out data from these big surveys?
Well, wow. I mean, think about Kepler. Kepler never downloaded its entire field. It only downloaded certain stars that were considered the most likely to be stable enough to give solid results on whether or not they had planets.
Is it just didn't have the bandwidth?
It took too much memory, too much bandwidth to download the whole field. So they only downloaded, I forget how many, I want to say it was 100,000-ish stars in the field, but there was a whole lot more data that got thrown out. Just all the details of stellar evolution. We have a big picture understanding, but it's really annoying that we can't, at a more refined level, understand things like one of the things that I started out studying as an undergrad, the Blazhko effect in our Alari stars, still isn't fully understood. This is an effect that causes the periodicity of a variable star. It's a secondary effect that changes the shape of the light curve over scores of days, hundreds of days. It's thought that maybe it's a magnetic field effect, but it still isn't fully understood. Why is this thing that could be understood with modern technology not understood? It's because it's not high enough priority to get the data that it needs. Other science that's sexier, like understanding the beginning of the universe, is awesome. But I'm the type of person that I want to fill in all the damn details. And we're missing so many details because we're so focused on what's the next big discovery.
I think one of the observatories, people are quite excited about all the new observatories coming out. And the one that I would say I'm most excited about now is the Large Synoptic Survey. Of all of the instruments that are coming, down the pipe, this one is really amazing to me because it looks at it'll see the whole night sky in about 4 days. So it's going to take a ton of pictures at a really high resolution, bordering on like the Sloan Digital Sky Survey. But instead of it being something that's done over the course of a couple of years, it's one that comes out every 4 days. And so you're going to see these changes in the sky. You're going to find Kuiper Belt objects, you're going to find asteroids, you're going to see variable stars, you're going to see attacking aliens, you're going to see, you're going to see all of this variation that goes on at night. You're going to see supernova, you're going to see all the stuff that...
But it's still unclear how much of the data is going to be retained.
Well, it sounds like because it's on Earth, right, they're just going to be pumping this data out and making it available. So I think
it's a data storage issue. So it could be that they're only keeping some sorts of the data. That's still being solved.
Right. Well, if that's what they're doing, then that's stupid. But if they're going to save it all, then that would be the way to go. Or figure out some way to kind of, catch the changes. But anyway, I think that's something like that will then allow a person who's got a question to just kind of look into the database and just go, I wonder if this information is in there. I found it. Right? As in exactly what you're doing. Like I want to find 1,000 different RLRA stars that are at different phases of evolution to really see what's going on. You could theoretically be able to do that and see what they look like every 4 days. So yeah. So that's I think going to be a really amazing observatory, and I think it's gonna create some discoveries of things that no one even had any idea they were going to see.
That's entirely true. We are going to find new phases, new events, new types of objects. And as far as it looks right now, they're going to be at least keeping photometry on everything that they find every night. So
you can get the light curve off of all this stuff.
So
we'll see what happens.
See.
So this is it. This is your chance. Someone built you an instrument. And of course, obviously, we need some kind of terrestrial planet finder. We need something that can detect the atmospheres of extrasolar planets.
Well, and one of the things to think about, though, is even with the every 4 day cadence, there's a lot of science that requires much more high speed, whether it be every 20 minutes, whether it be every 20 seconds. And one of the problems that we're running into in science right now, which is one of the reasons I answered the way I did, is we're throwing out the 1 meter telescopes. We're throwing out sometimes the 4 meter telescopes because we don't have the money to maintain the systems. And we're moving into an era where we're either doing an all sky survey, which is a snapshot of the entire sky, or we're doing 3 nights on this object, 3 nights on this other object. But we're not doing that long-term monitoring that you used to see when everyone had their own 1 meter not everyone, but lots of people had their own 20-inch, 30-inch telescope, and people did sit on stars night after night after night. That let's study this one small field forever that Kepler's doing used to be something that you'd see much more often, looking at globular clusters, for instance. And that's just not happening anymore because we don't have the smaller telescopes anymore that can dedicate their time to that kind of science.
Yeah, I read a research a study a couple of years ago, and they were saying that they could find planets around Alpha Centauri, which I know now has been confirmed, with a 1 meter telescope. You just pointed at Alpha Centauri for 3 years,
right,
nonstop, and with that much data, you would detect the planets, or at least I think they said an Earth-sized world around Alpha Centauri.
Yeah.
And so a great use of a 1 meter telescope, or you could do it in a fraction of the time with a 3 meter telescope, right? Let's see if we've got some questions, not just mine. Guido Bieber notes that it's Happy Towel Day. Is it Happy Towel Day?
I have no clue what Towel Day is.
From The Hitchhiker's Guide to the Galaxy.
It's not 42 in any direction.
Let me see. Monday, May 25th. Yes. Yep. On this day,
was that the date? Was that the date in the book?
It was held. No, it was 2 weeks after his death on May 11th, 2001.
Okay.
So, and for anyone who doesn't know why a towel is relevant, it comes from
read
Hitchhiker's Guide to Hitchhiker's Guide to the Galaxy, with the gist being a towel is the most useful thing a hitchhiker could ever need. It could be used to keep you cool, keep you dry, keep you warm, protect you from bugs.
Didn't they have, I want to say it was flavored somehow? Or am I combining that with something else? I haven't read the books since he died, so.
Yeah, there's a great sort of chunk from the book about it, but look it up. Look up Towel Day on the internet, on Google, and you'll get it. Steve Chisnell asks, have you heard about Alvin Weinberg's efforts to research molten salt reactors?
No.
Relevant to astronomy because the reactor design he came up with would have been particularly good for powering a prospective manned lunar base. So, molten salt
I'll have
reactors.
to look into that.
Yeah.
Molten salt just seems like a really bad idea in terms of something to have around a human.
It's where the primary coolant or the fuel itself is a molten salt mixture. They run at higher temperatures than water-cooled reactors for higher thermodynamic efficiency while staying at a lower vapor pressure. Did that make any sense to you?
Yeah, it's using uranium salts.
Yeah. And so I guess you use the salts to be the coolant, and that way you can run it a lot hotter, and you can then get more energy out of it with less heat loss, which is always good. What else have we got? Ed Thompson asked, did we get a chance to look at Saturn while it was in opposition on Saturday evening? No.
I was sick. I've been fighting bronchitis. I seem to have mostly defeated it, but
I'm definitely seeing Saturn. I mean, yes, with my eyes. It's just great. I mean, have you seen the moon with Venus and Jupiter in the evening sky? It's great. I mean, Jupiter and Venus are starting to get closer and closer together, and every time the moon comes through, it's just great. I'll have to go on another one of my my things on Twitter where I tell 1,000 people that no, those aren't stars, those are Jupiter and Venus. I like to do that on every big conjunction.
We've also been having thunderstorms and tornadoes here, which kind of makes it hard to observe. Last night we had this amazing lightning storm that was quite dramatic.
Yeah, my girlfriend's is from Texas, and she was looking at some of the weather patterns that are going on there, and they're just getting blasted with flooding, and then there was like these crazy like tornado warnings at the same time. Yeah,
that's not unusual, but the flooding they're having after so many years of drought, the land just can't absorb the water. Yeah,
you see these pump jacks that are just barely above the water line. Like there's must be 15 feet of flooding in the area.
Yeah.
So Steve Chisnell also asked, did Richard Feynman have a rather low opinion about string theory?
Did string theory already exist before he died?
I don't know. Do I have a quote? Both Googling it. He criticized string theory in an interview. Let's see what he said.
So string theory started to come out in 1943. So yeah.
Wow. He said, I don't like that they're not calculating anything. I don't like that they don't check their ideas. I don't like for anything that agrees with an disagrees with an experiment, they cook up an explanation, a fix-up that says, well, it still might be true. So
that I hate agreeing with Feynman because he was kind of an asshole, but
yeah.
I agree with all those statements.
Yeah, it's you know the you always have to say Feynman, and then you have to sort of put an asterisk and note that he was the
Asshole.
misogynist asshole. And
yes.
But specifically, the kind of asshole was a misogynist sort of.
Yeah, one should never try and steal their graduate students' significant others. That just.
Nancy Graziano notes, would be surprised to discover that there is yet another sub-elementary particle layer below what we currently know. Or do you think we have the atom completely broken down?
I don't think there's anything smaller than the quark that we're going to figure out, like things that build the quarks. But the theory of supersymmetry, which currently doesn't have any evidence backing it up, it postulates a bazillion new particles. So there might be more out there.
But it's making predictions, and
yeah,
the Large Hadron Collider is
achieving energies that should start to be able to prove or disprove. There's
like
actually certain
week.
There's certain flavors of supersymmetry that have already started to be ruled out by the lack of things being discovered by both Tevatron and the Large Hadron Collider. Tevatron being at Fermilab. It's the other high energy collider that hit the high energies first, went down for reconstruction. Large Hadron Collider's now picked up.
So, but it is like a whole other order of magnitude to actually confirming, say, string theory. Like it's a whole other, or many orders of magnitude, right?
String theory actually doesn't have any completely exclusive predictions. So you can't at any point say string theory is the only explanation for this based on predictions made by string theory. That's one of the things about string theory that causes me to just sort of go, nope, I'm out. Is this lack of any independent verification that's possible.
Steve Chisnell notes, so maybe what's needed, this is back to sort of what we were talking about earlier, what's needed instead of a single large telescope, do we need maybe produce and install a large number of observatories with identical 1 meter mirrors to conduct coordinated observations like Kepler, but on a wide variety of objects?
I think
yes, right?
We need a whole variety of different observatories. One of the problems that we're having right now is something like a third of the nation's astronomy budget goes into ALMA, LSST, Curiosity, and James Webb Space Telescope is on top of that. So we're basically spending vast sums of money on these 4 facilities.
Mm-hmm.
And this is meaning that we're having to close down lots and lots of other facilities along the way. And the science that can be done with small telescopes just isn't being done anymore except by amateurs. And there's not enough of them there's only so many spousal permission units you can burn through.
When you buy a 1 meter telescope.
Yeah. And going out and observing every single night and then going to your day job as whatever your day you amateurs can do amazing work, but they can't fully fill out the gap simply because they do have day jobs.
Yeah.
So what we really need is the budget to go back to having that full suite of telescopes at all different size ranges where you can have the scope that's dedicated to, I'm going to go out every night that's clear and observe this one star or this one globular cluster. We don't have that capacity right now. Yeah.
It's a funny time, right? Because we're at this place where everybody loves the pictures, the amazing pictures from the Hubble Space Telescope, and NASA and all the space agencies have really enormous social media feeds. We see it with even with what we do, right? We have lots of people that like to listen to what we're doing, the weekly Space Hangout. I'm getting lots of subscribers on the YouTube videos that I'm doing. So there's a real demand for this information and for us to push the science and an enthusiasm for it. And at the same time, there's this budget getting cut and facilities are being closed down and it's this really strange thing that there's this disconnect between the admiration and appreciation and recognition of science and especially astronomy and what it means for our daily lives, and yet there isn't this from a governmental level sort of capturing that zeitgeist in a way that you would expect. You expect the two to be roughly in line, but they're just not.
And one of the problems is that there is this mistaken belief that there are huge sums of money being spent on science, and there's not. And so when you ask people how much of the US budget do you think goes to science, they'll spit out numbers in the tens of percents, and it's not. And then when you ask how much you think is going to astronomy, they'll still assume several percent, and it's far less than 1. And this mistaken understanding of how much money is being spent leads to people not seeing a reason to increase spending.
Yeah. I don't know. We'll see. I mean, hopefully we'll start to see these alternative methods of funding starting to grow on the internet where people are pooling their money and helping to contribute, and citizen science projects like what we're doing. So I think there's...
It's not a complete answer though, because you're going to perhaps be able to get up to, in some cases, the $1 million range. I mean, the Allen telescope that SETI has put together is one of those examples of building a full facility off of donations. But when you're looking at organizations like NASA, you're looking at needing billions of dollars. And we're not going to get there readily through Kickstarter.
No, but you said, that you don't need billions. You only need millions. You'll need hundreds of thousands to operate some of the smaller facilities, to operate these 1-meter telescopes that can get a lot of work done. That's the kind of thing that people can raise funds for to get those operational.
But you need multiple of them is where it starts to be a compounding problem. And it also gets once you have the facility, you have to pay the salaries. And
Yeah. So I just think that we're closing in on a time where regular people can pull together. If science is important to them, they can contribute to it. And I think they can make the sort of help push science forward. And I mean, even just like donating to CosmoQuest, right? Donating to what we're doing is a way to kind of take... If you love science and you want more of it done and you want to contribute directly to the science getting done, either just give your time, like go into CosmoQuest and start mapping craters and start actually being a part of the scientific process. And if you don't have the time, then give the money. And the other one, there's another question here. Douglas Friday wants to know what's the deal with the Astronomy Cast Patreon. It's coming. We see time. But there, if you contribute to CosmoQuest, you're contributing to Pamela's salary.
Yes, that's
right. And that allows her to do more astronomy outreach as opposed to working in a Starbucks.
Yeah, no, it's literally at the point right now. I have 2 large grants pending, and if I don't get one of those 2 grants, I have to find a new career. And that's how bad it is right now. And
it'll be computer programming, I think.
Probably not, because I think writing software for other people would kill me. But
yeah, and it's the same thing for me, right? I mean, you come to Universe Today and you read the articles, you and especially you contribute to my Patreon, and that allows me to hire the writers. It allows me to keep doing the work that I'm doing. Patreon.com/Universe Today.
And we do have Learning Space, which helps with my salary starting in July. So Learning Space on Patreon is another one of our projects.
Yeah. But it's a funny thing. So anyway, we'll keep going. We'll keep getting the science out there and contributing to it as much as we can.
Yeah.
And this was the, CosmoQuest was the scale of the science that we thought that we could do. It was the way that we could get the enthusiastic public involved in actually contributing to the science. So,
yeah.
Tom Nathan says the crowdfunding is a voluntary tax towards something that you like. I think that's exactly right.
Yes.
Richard Clark asks, when is your last show before your break? So
we haven't decided yet, but it'll be sometime around 4th of July.
Yeah. And then we'll be back after the Labor Day.
Yeah.
I'll be at PAX this year. So that'll
you're doing that instead of DragonCon?
Yeah, they have to share custody of me. So last year was DragonCon. The year before was PAX. So this year I'll be at PAX with the kids.
Cool.
So if you're going to be at PAX, look me up.
I'll be at DragonCon. So pick a coast. We've split the country.
There you go. Yeah, and Steve Chisnell's got all kinds of great ideas about how we can crowdfund 3-meter telescopes. That'd be interesting. I wonder if you could set up 3-meter telescopes in people's backyards, make them computer controlled, and
yes. Falk's telescope has worked to do that at schools and other facilities. It became the Las Campanas project. It ends up costing a whole lot more money than anyone originally thought.
Oh, this is a surprise. All right, well, it's 1 o'clock here. Well, let's wrap this up. So, Pamela, thank you so much. Everybody, thank you so much for watching. I just want to give a couple of quick suggestions. If you want to at least talk to other people that share your worldview, there's kind of 2 places that I really think you should go to. One is the CosmoQuest forum. This is cosmoquest.org/forum. This is the long-running forum that started as the Bad Astronomy Forum, and then the Bad Astronomy Universe Today Forum, and then became the CosmoQuest Forum. A great place, and a lot of sort of people who've been talking about this thing for 15 years. And the other place to go is the WSH Crew, and this is a community that's gathered together for the Weekly Space Hangout. And what's great about that is that they literally are the producers of the show. So they now choose the stories that we talk about on the show. And they also schedule the guests that we have on the show. And we've had some great guests. We had Baz Lansdorp from the Mars One project. We've had
Andy
Weir from The Martian. We had astronaut Ron Guerin. So we've had some great guests, and it's been a real treat to that. So if you want to join that community, very small, very tight knit. It's on Google Plus. Just do a search for WSH Crew in the communities on Google Plus, and they'll be glad to sort of share your enthusiasm for space and astronomy. All right, cool. So Pamela, let's wrap this up. Thanks everyone for watching, and we'll see you all on Friday, I hope.
Yep. See you all on Friday.